We're going to start in a couple moments, and I would love to have someone volunteer to scribe, to take minutes, and someone volunteer to be Jabber scribe. Do I have an offer of scribing skills? Okay, thank you. I didn't even have to offer a bribe this time. Hello? Okay. Okay, let's start. Andre, we're starting. So good morning and welcome to IRTF Open. I'm the IRTF chair, Allison. And I think it's Wednesday morning, so we're already like really tired and jet lagged and not getting enough sleep, so pay attention. We have a new note well in the IETF, and the IRTF follows the IETF's note well. So this is our version of it, which isn't very different, but just you should be aware. But if you haven't read this new one, because it's just getting rolled out, do take a look at it. And in addition, as you know, there's a photography consent discussion, and the IESG has made a statement on this. Because we actually do have a lot of photography in here because of the ANRP, I want to make sure people know that if you don't want to be photographed, there will be the video, but you have the right to consent or not. And you've got your lanyards, but also let us know if you have any worries about that. Okay, so I just have a couple of things to say about IRTF before we get started. This is the sort of longer term part of the organization, and we definitely have an interest in well-focused research that results in things that innovate for the IETF. The idea here is to give people the opportunity to see their research get into action, and it's a time to incubate that. And I'm sure you know, because you've been coming to research groups, that we have research groups. Last time, if you were here, I talked about how they're different. I'm not going to talk about that this time. And that we have an IRSG, and their names and all that information is on the irtf.org page. And I've noticed that some people don't seem to know this, so I've added it, that IRTF does not produce standards. We're pre-standards. So to the extent that RFCs come out of the IRTF, they come out as experimental or informational, and they're meant to say very clearly that this is research, and then one reason to have them in an RFC form is that later they may evolve and migrate into research, into results that are used in standardization, but not in these research groups. So just that's something. And here's a list of all the research groups. We have this concept of proposed groups, and the idea is that it should be quite easy to spin something up because it's not always easy to tell when what's new and what's a good thing to work on. So we allow a group to form very readily, unlike the working group chartering process, but it gets 3 meetings, and then the IRSG and I decide whether they'll continue or not. So we've got a couple of proposed groups in process now. The DIN group, the Decentralized Internet Infrastructure, which really should be called D instead of DIN, and Path-Aware Networking. And then we have 12 groups altogether, counting those 2. Path-Aware Networking had their 3rd meeting yesterday, and we had a hum. We do actually hum if we can, because who doesn't want to hum? But the agreement by the group, by the room, was it should go to RG, and I believe it will. So that's something. Another bit of news is that when our group Gaia, which is the internet access to the internet for all globally, is they've helped to organize with the IAB the technical plenary tonight. So there are 3 Gaia-themed talks, and they're moderated by Jane Coffin, who's one of the co-chairs of Gaia. And then this week, everybody's meeting except the network management group. We do feel that groups should meet with research conferences as well sometimes, and they regularly meet with the NOMS conference, and that's what they're doing. And then today you're getting the first look at a potential new group, which is the Quantum Internet Research Group. And the goal here is to have you eventually have to start calling yourself the classical internet people if you're not working on quantum. So we'll see if you're convinced of that, but we'll have a remote speaker on that shortly. Okay, so the other thing is I want to advertise the workshop. We have a workshop that tries to bring academic research and our standards and the applied research we do here all together. It's been happening for several years now. It takes place during the summer meeting, and we have an innovation this year, which is that it will take place during one of the IETF days. I'll talk a little bit more about that at the plenary tonight. The idea is to try to bring more togetherness between the people who come to talk about applied research and the research groups and working groups themselves. And you probably have something you'd like to submit. It's due by April 20th, so please think about submitting. It's really easy to find if you look up ANRW 2018 or look at the IRTF page, you can find it. The good thing is that you can either submit a short paper, like a couple pages of something that's sort of hot and new, or you can submit a previously published paper from the past year. So you don't have to write a brand new, deep 12-page research paper. You can bring something that you've done somewhere else to this workshop. And they've been very good, and we're hoping they'll be even better and even more exciting because of the bringing it closer together to the rest of the meeting. Okay, so these are some of the links if you want to get more involved. You probably already know IRTF Discuss and Announce. And we have wiki links for all the research groups that you can find at irtf.org, some mail, we tweet. And the agenda for today is, I'm almost done, and then Rod Van Meter is going to speak. Stephanie has a family issue, so she will not be joining us. But we are hoping, these are the 2 proponents for that research group, and Rod will tell you about how to get more involved in that. And then we have our Applied Network Research Prize talks, and I'm very excited about those, and I'll introduce those when we get there. So I think we're going to try to bring Rod on. Oh, no, let me tell you about the NRP. I'll use this slide when we come back, I think. No, let's do it now, sorry. So we have our 2 speakers coming. We are sponsored. The ANRP provides a monetary award and travel funding, and the sponsors that make that possible are Comcast, NBC, Universal, and the Internet Society. So thank you. And if you think you'd like to sponsor, please let me know. Get in touch with ISOC or myself, Matt Ford or myself, because if we get more sponsorships, we'll bring more people back for additional meetings to allow increased engagement. And I wanted to say also that we have a wonderful program through the year. We have 2 each IETF. We had the largest set of submissions that we've ever had, and we could definitely have made many more awards because we had so many good submissions. So I think you're going to have a good time with our presentation. So, and that's it. And that picture is to tell you, don't be like that cat. Don't read your mail, engage during our meeting. And it's particularly actually for the research group chairs who should look around, and if you see people being like that cat, you probably need to get more discussion going. That's my cat, but, okay. All right, so let me see if I can get us to Rod now. It'd be useful if that didn't, okay. So let's see, I have his slides. So Rod, can you speak? Yes, hopefully.
Yes, can you hear me?
And I think I'm going to be showing your slides probably.
Yeah, I'm told you're the one who gets to run the slides.
Okay, let me bring them up. Okay, go for it. I've got your title page slide. Tell me when you want to change.
Okay, great. So thank you all for having, and I'm sorry I'm not actually there in person. I would love to be in London with you all, but in solidarity with the weather having there, we're actually having snow here in Japan, actually in Tokyo too, for the first day of spring. We planned this presentation. Allison asked us to give the presentation based on some email that she and Stephanie and I had exchanged over the course of the last, 6 or 8 weeks, I guess. And I want to tell you a little bit about what a quantum internet is and what we're thinking about, and ultimately why IRTF should care and why IRTF should actually charter a working group, and tell you how you can get involved and what kinds of things that people in the room there can do. So as Allison said, I'm Rod Van Meter. I'm from Keio University and the WIDE project, so I actually probably know a significant number there in the room, although I can't see who's there very well. And Stephanie Vayner is from the Technical University of Delft. This was actually originally her idea. And she used to work for one of I believe for an ISP in the Netherlands before actually getting involved in quantum work. So she and I both have a long history with actual networking as well as quantum stuff. So that's where we are. Allison, can you go to the next slide, please?
I have.
Okay, so the one other person I should probably introduce while we're looking at this slide here, I think somewhere in the room is Shota Nagayama. Shota, can you wave your hand if you're there somewhere?
Hello.
He may be around
He's
somewhere.
doing that.
Okay, so Shota was a PhD student of mine. He is actually also a participant in IETF. So he's one of the other people who actually sits right at this border of quantum and classical stuff. So after I go offline here in an hour or so, you can track down Shota there at the meeting in London and talk to him about it. So first off, I should say, what is a quantum network? And I know a lot of people in the room are already familiar with quantum key distribution. Quantum key distribution is a way to use quantum effects to create a shared sequence of random bits that the physics of the system is supposed to guarantee you are known only to the two parties at the endpoints. And then you can use that set of random bits for a key for IPsec or TLS or what have you. That's the easiest way to implement QKD is actually using what we call an unentangled quantum network. So it uses single photons, but you don't actually have to have complicated memories and a complete quantum computer that serves as the equivalent of your router. If it works, it adds to the longevity of the secrecy of your encrypted information, but it works only over a limited distance. 100 kilometers or 200 kilometers through fiber, but in theory, it also works over satellite. In fact, there have been demonstrations of that over the course of the last couple of years. It's sort of weak in multi-hop settings, but better for point-to-point. It's a lot easier than building entangled networks at the physical implementation level. It's still not very easy. So a lot of you are probably already familiar with the basic idea of QKD. You've heard us or somebody else talking about it at some point. That's only one of the applications that we actually envision for networks in the long run. But those other kinds of applications that I want to tell you about require what's called an entangled network. I'm not going to go into the details of what's going on at the physical level, but basically it means that you're creating a shared quantum state over a distance. And so the work of the quantum network then is to actually create that shared quantum state. Entangled networks are good for a set of applications. I'm going to show you those a little bit more in the next slide. And in theory, using quantum repeaters, which are not like classical repeaters. A quantum repeater is more like what in the internet world we would call a router. Using quantum repeaters, we can, in theory, couple together systems that are an arbitrary distance apart to within sort of the normal limitations of networking, as opposed to the distance over which you lose a single photon, which is the limitation in unentangled networks. Allison, next slide, please.
Okay.
So on this slide, I've actually got a view of how I think about the applications for entangled quantum networks. There are three large bubbles there. The purple one is distributed cryptographic functions, the blue one is sensor networks, and then the yellow one is distributed computation. You can see sort of on there on the Venn diagram that there are a set of potential applications. QKD is in the middle on the right. It sort of sits at the border between sensor networks and distributed cryptographic functions, because really what's actually happening with QKD is it's behaving as a type of sensor and detecting the presence or absence of an eavesdropper in your communication channel. So that's one potential use. Another one or two in the distributed cryptographic functions up there, you can see at the top of the center, are Byzantine agreement and leader election. And if you look at Byzantine agreement and secure leader election and quantum key distribution, sort of the point of all three of those is to reduce our dependency on public key one-way functions and computational complexity as the basis for security first. So that's one potential area for the uses of quantum networks. In the lower right, sensor networks. Besides QKD itself, there are two or three other good uses for sensor networks, and many more are being proposed. Clocks is one of the important ones. Clock synchronization, there have been several algorithms proposed for doing this using quantum effects that would, in theory, gain us synchronization of clocks over a remote distance that's at a much higher level of precision than what we can achieve today using GPS or NDP classical method. So that clock actually is a form of reference frame. It gives you, it tells you what the time is in a couple of different places. It allows them to essentially synchronize the axis of time. But distributed quantum states can also, in theory, be used as a reference frame in the physical sense as well. And so people are investigating different kinds of sensors for that. And also for what's called for interferometry, which is how large-scale astronomical installations collect light from multiple telescopes or multiple radio antennas and combine them into a single signal. So at that level, it's very much a physical level operation that's going on there. And then in the lower left, the third circle, the yellow one, is distributed computation. And this, in this sense, is largely like the ARPANET. This is a distributed system in which you actually connect to and use servers over a long distance. And the idea is that even if you have a computer that isn't very capable at your site, that you can connect to a quantum mainframe somewhere else out there in the world and be able to use that quantum mainframe remotely over the quantum network. Now, why is that different from just being able to do what you can do today, which is log on to IBM's website and use a quantum computer that's sitting in Yorktown Heights remotely via the web? Well, if you begin with quantum entanglement between your site and the mainframe, then it's possible to do what's called blind computation. And the blind computation is a mechanism for asking a server to execute a function for you without giving the server any information about the input data, the algorithm that's being executed, or the output data. So it's like Gentry's homomorphic encryption in terms of its role in the ecosystem, although the underlying technology is very different. If you're familiar with homomorphic encryption, you can think of it in kind of the same use. So those are the three broad areas in which I can see uses for a quantum network: distributed cryptographic functions, sensor networks, and distributed computation. Okay, Allison, next slide, please.
Okay.
So I mentioned a minute ago quantum repeaters. Quantum repeaters are the equivalent of routers in the internet, and they have four basic tasks, which are listed up there on the screen. First is to the basic entanglement, the basic quantum state over a single hop, over a fiber, or over a free space link. The second task is to manage the different kinds of errors there are, including the loss of the photons and inaccuracies in the operations on your quantum states, and the fact that memory has limited lifetime. The third task is to extend entanglement across multiple hops, so the behavior of a network. And then the fourth task is to actually be part of that network, including dealing with routing and managing resources and security and those sorts of things. And it's in particular those last couple of bullet points that I think folks that are there in the room are likely to be able to make a positive contribution toward. Next slide, please.
Okay.
So that gave you just 3 minutes on the why. What is it that we want to accomplish by doing this? The next thing I want to do is to sort of give you an idea, give you a sense of what's going on in the world and the fact that this is in fact happening. On the right-hand side of the slide there, you can see just logos from 5 startup companies that have been around, most of them for a while now. But overall, in the quantum information industry, there are now more than 50 startups. Many of them have been created within the last year. Some of them are hardware companies trying to build quantum computers. Some of them are software companies trying to figure out how to use the existing quantum computers. And some of them are networking companies. These that are here on the slide are all QKD companies. As far as I'm aware, none of these companies are actually working on quantum repeaters yet, but that may very well be internal efforts that they're not actually talking about in public. So it's happening in the startup industry. It's also happening in the big labs. IBM, Google, Intel, and Microsoft getting a lot of attention for their work. And there's also venture funding that's out there. There's also, of course, a lot of support from government And so there's an entire complete ecosystem of people who are working to create a quantum information technology industry. And I think you can argue that in fact that industry already exists today. So the technology, the knowledge, and the ecosystem are all reaching this point where we are sitting right at the edge where this whole thing is going to blossom, and over the next several years you're going to see a lot of actual use for quantum information technology coming out. Now the quantum repeaters is arguably the hardest part of all of this, and so it's going to be a little bit while. It's going to be a little while yet before quantum repeaters are here in the wide world as something you can go and buy off of the shelf, but that's what we're working toward. Next slide, please.
That. So
Stephanie's really the one who ought to be here to talk to you all about this particular slide, because she was one of the leaders of this particular project at the Technical University of Delft, just a few hundred kilometers from where you all are right now. A couple of years ago, this paper was published in October 2015, pushing on 3 years ago since the experiments were done. The folks at Delft took two tiny pieces of diamond that were set about 1 kilometer apart and coerced them to hold qubits, quantum bits worth of data inside that tiny chip of diamond, and also to emit photons. And then they take those photons and they route them together, as in the diagram at the bottom of the slide there. And then they conduct an interference operation between the photons there in the middle. And once that's done, then they have created this quantum entanglement over this distance of 1.3 kilometers in the across the Delft campus. So this can be done today in optical fiber over modest distances. It's experimentally up and running, and the group at Delft is arguably the world's best, but there are a lot of people who are working on similar sorts of things. Next slide, please.
Okay.
So besides just doing this using fibers that are actually in the ground or in buildings in between, there's also been work on doing this using satellites. And you may have heard about this and made a tremendous amount of news last summer when China announced that they had succeeded in receiving quantum signals on the ground from satellites that they put into orbit. The very first experiments that were done were essentially QKD, between two stations on the ground. They're separated by about 1,000 kilometers or so. But later, they continued to conduct experiments. They had already prepared for them there with the satellite, and they continued to conduct them. And they have actually generated entanglement across that kind of distance. And they have also more recently used a slightly different approach where the satellite is actually used as a relay station. And so it performs QKD between the satellite and the ground when it flies over China, and it stores the classical bits it has created in the process in the memory of the satellite. And then when the satellite's orbit carries it over Austria, then they perform QKD again between the satellite and Austria, and then they have created a secure key that's shared between Austria and China. Now, this was actually in the news quite a bit last summer or last fall when they talked about it and used the key that was so generated to encrypt a conversation between China and Vienna. So it got a lot of press. We can talk about the actual security implications for all of that and whether or not you have to trust the satellite platform and things like that for QKD. But when you're actually using it, excuse me, for creating entanglement over this kind of distance, then those kinds of security arguments are actually very different. And so please, you're already of a particular mind with respect to QKD in certain senses, realize that the arguments are going to be very different with when we're talking about wide area networks that actually provide entanglement end to end. And China's not alone in doing work on this. There have also been experiments from Canada and Singapore, and the other picture there on the right in the upper part is actually a satellite that's in orbit right now that was put up there by Japan last year as well. So satellite work and also ground-based work is going on this. Next slide, please.
Okay.
And ultimately, there's work going on all around the world, but Europe right now is one of the places where there's a tremendous amount of not individual effort, but very focused effort. So the EU has a quantum internet effort that's known as the Quantum Internet Alliance. There's a logo for it there on the left, and a URL, quantum-internet.team. And you can see, by going to that website, you can see the list of researchers who are involved in this. Stephanie, again, is one of the prominent researchers that's involved. So I wish she were here to tell you more about it. But it's part of the EU's overall €1 billion effort to develop quantum technologies and bring them out of the laboratory and into the actual market. Next slide, please.
Okay.
So what does it take to actually build one of these networks? This slide comes from a paper that I wrote fully a decade ago on protocols for quantum repeaters. And you'll see that there's sort of a stack. Many of you who are in the room probably know Joe Touch. Joe Touch and I argued about this quite a bit over various meals and visits to each other. The upper layers, everything except the bottom, is actually a classical control protocol. So at the bottom in the purple box, you see it says physical entanglement, and red letters there, the only quantum. That's the only part of the entire system that's actually physically quantum. So everything else that's above it is classical protocols for controlling the behavior of this quantum system in order to go from having entanglement that exists over a single link to entanglement that actually spans end to end from your communication endpoints. Now, the protocol stack that's above it involves a series of functions which are going to depend on certain key design decisions from your general architecture for your quantum repeaters. But this is a reasonable example. Some of it happens over a single hop. Some of it happens over 2 hops or 4 hops along the path chosen through the network, and then some of it's done end to end. And that's where the argument with Joe Touch comes in is, all right, well, maybe it's not really a layered protocol in the sense that the IETF is accustomed to things. It's actually much more of a distributed computation because all of the individual nodes that are in the path actually participate very actively in the entire process as you are conducting your communications over an extended period of time. So it's a very different approach than the internet's fire forward and forget approach to building a protocol. But this is an area where classical protocol design people can make a very strong positive contribution because of the expertise in doing these kinds of things. And that's it. Yes, so Allison, perfect timing to switch to the next slide there. So we are getting to the stage of wanting to take all of this and to discuss these kind of the important problems in a network. How you deal with routing and how you deal with connection setup and how you deal with resource management and how you deal with inter-network interoperability and security and all these kinds of issues, which are near and dear to the hearts of the people that are there in the room at IRTF. And the experimental physicists who are doing the work so far have no idea how any of this stuff is done. They don't know how to go about setting up a connection between two nodes across a network. They don't know anything. How you do resource management in a wide area network. They may know, what multiplexing means in a single channel, but not so much across an entire network, for example. So we need the expertise of the people in the room, and we need a way to connect classical networking people to the experimental community that's beginning to build these quantum repeater networks. Stephanie proposed 2 or 3 months ago that we should create a research group inside of IRTF. So I contacted Allison, and we've been exchanging some email about it. And so far, the proposed name is QIRG. The mailing list is open. You are welcome to join the mailing list. There were a couple of dozen people on it already, even though we're just beginning the process of advertising it. So please get on the mailing list. And Allison, next slide, please.
Done.
Whoops. Okay, this was not the. All right. We'll do this. I did want to mention briefly as we're finishing up that there are also QKD-oriented standardization efforts both inside of ETSI and IEEE. And of course, inside of the IETF, we have been talking off and on for 8 or 10 years about methods for incorporating QKD-generated keys into IPsec and dealing with other out-of-band key management mechanisms or key generation mechanisms. So there's work that's going on that as well. Next slide, please.
Got it.
And the first task, if you join us in the QIRG mailing list, is maybe perhaps somebody in the room there can suggest a prettier name than QIRG, which we haven't even yet agreed on a pronunciation for. We're not sure if it's Churg or Quirg or what it is. We understand some of the elements that are going to be in the charter. There's some of the things that I mentioned on the previous slide a minute ago, but there's, of course, work to do to hammer out the actual content of that. And the tentative plan is for QIRG to meet 3 times a year. Once at IETF, once at some sort of quantum conference, either QCrypt, which is a QKD-focused meeting, or the workshop for quantum repeaters and networks, which is a repeater-oriented workshop, and then to have one meeting be virtual. So to meet 3 times a year on that schedule. And that's it. Let's see. Next slide, please.
Yep.
So we will be having the next of the WQRN workshops actually here in Japan in fall of 2019. And if you are on the mailing list, of course, you will get the announcement. You'll be asked to join up with us on that. And with that, I hope that you all are as excited about building a quantum internet as I am. And, Allison, I guess we have time for questions.
I think there's time for a few questions if people have any, and hopefully you'll hear them well. And say your name when you come up.
Hirotaka Nakajima. Thanks for the talk. I have one qualifying question and one question about classical network and the quantum network. So the first question is, so according to your slide, page number 9, it's like there is no IP or TCP. It's a classical network stack. But your figure says like that only a bottom layer is that quantum network. So I think we can it seems like there is a new, different network, and we are trying to create the quantum network instead of the classical network. So is that my understanding is that we will create a new network. Is that correct? That is one qualifying question. And also the second question is, so if the quantum network we cannot use IP or those classical network stack, so in this case, like it's a little bit hard to connect or communicate between the classical network and quantum network. So is current scope, the charter has some kind of work to achieve the communication between classical network and the quantum network?
Yes. So hi, Nundan. How are you? So those are good questions. So Alice, if you can go back to that slide briefly, the one with the colored stacked boxes.
Yeah, the stack slide. Got it.
Yeah. We are going to have a new physical layer. So there's no getting around that. That's going to mean deploying new devices with new transceivers or the equivalent thereof. There is work going on to allow that to multiplex with standard TCP/IP traffic inside the same fiber. That's been demonstrated experimentally. So you need new nodes, but you don't necessarily need to pull completely new fiber in parallel. All of those other functions that are on top of that are all new protocols, but of course they also need a means to exchange their classical messages reliably. So when I picture the protocols PC and ESP, I picture those communications actually happening over top of TCP, and then the application layer on top of that is what's the equivalent of an HTTP put and get or for a quantum network? What is a request from an application to the network itself? What is it that a classical application that's running on a node that wants to take advantage of these services provided by the quantum internet? How does it make that request? What does that contain? How do you exchange that, and how do you agree on the semantics of all of that? So those colored boxes that are on there, I think largely will ride on top of TCP in terms of the actual communication that gets done. But it's building a large distributed application on top of it. Does that help?
Yeah.
Okay.
Thanks.
Great. One more question. Or two more.
Wes Herdeker, USC ISI. Originally I was thinking that this was a little bit early in thinking, but then I decided that I'm wrong there, and we want to get this sort of right from the get-go in terms of the research output of something like this could actually affect the development of the hardware and the techniques. So I think that's actually the timing's about perfect. So I'm excited to see this go forward. I do think that there's a few other topics you could consider adding to your list of things to explore, such as the security requirements for what's going to be layered on top of it, in particular with respect to privacy concerns. As an example, your satellite is sort of a classic case of a store and forward mechanism where you have to store data at rest while it travels, or interplanetary networks have the same kind of thing. And excuse my ignorance of quantum stuff. I'm actually fairly ignorant, and it may show. But so the quantum routers have a similar property where since you're essentially breaking communication between in the middle between endpoints, then you're disturbing the privacy that I believe is offered by quantum generally. So, what's the security implications of that? So I think there's a number of things that need to be considered with respect to what sort of technologies you need above that and the requirements above that. Do you still need to do, send, what sort of encrypted traffic do you need to send above that, and what are the properties of the protocols that you're going to use on top of this whole system that you can either relax because you have quantum, or you still need because quantum doesn't solve them?
Absolutely, sign that man up. And given given that I'm an old Div 7 person from ISI myself, I'd love to have you on board because that'll give me an excuse to go back to ISI and see the gang.
Okay. One more question. Shota.
Yeah, actually, Shoto Nagayama is speaking. So actually, this is not a question, just comments. So yeah, now the research of the quantum networking requires the organization of terminologies, I believe. Yeah, because some papers start to propose some different terminologies for a single same concept. So I need a place for open discussion. For such things. Otherwise, so various papers which use these different terminology will lead to a kind of hell. So to avoid that, we need we need an open discussion. So IRTF is the best place, I believe. So and we can refer classical network terminologies properly here. And so another thing is one thing we need to discuss in IRTF is the abstraction of the entanglement. And so entanglement is a very quantum property, and classical networking doesn't have the counterpart for that. So we should carefully discuss the abstraction of entanglement. And at last, so one thing, so the one benefit to talk about quantum networking in IRTF is that who will administrate quantum network in the future? So it will the network engineers, so like guys here. So to involve such people for discussion of quantum networking is very important from this early stage.
Thanks. Actually, I agree with all of those comments. In particular, Shota and I've had quite a bit of heartburn with where the physicists reuse a term they have from classical engineering, and the way they're using it is not necessarily wrong. It's just so different from the way we're used to using it that it's causing a problem. Multiplexing is one of them. Repeater would certainly be another. And of course, they also when they say the physics of this guarantees that it's secure. The head of every network administrator in the room hits the desk because they know that theoretical factors of implementations are very different from the real world implications. And so doing all of this and discussing all of this with the people who understand real networks is the key to a long-lived, healthy, robust, extensible quantum internet architecture. And I think that IRTF has a lot of expertise that's really required.
Yeah, we've got one more question and then we'll stop. No more questions. Mariko.
Hi, I'm Mariko. Actually, I'm not so familiar with this area, and so this is comment related to this community. And I'm not I am sure quantum computing is important for network engineering and from now on the future. But I think there's not so many people who are familiar with this area. So, so if you will work on this quantum computing discussion in this IETF area, how do you get IETF network engineers involved in this discussion? And also, how do you link the quantum computer guys from outside this community into this IETF community? So how about your plan for that?
So the social.
Well, the plan definitely starts with the creation of the QIRT itself. That's the forum for bringing everybody together. I was pleased to hear the earlier comment that I didn't catch the name of the guy from ISI that I don't know, who said that now he sees that maybe now is the right time to it's a good opportunity for people to be involved to prevent the physicists from going down the wrong path. Now, convincing the physicists that they need to be involved, that's the other half of the equation, and we're working on that one too. But there are already hundreds of researchers around the world who are actually working on this, and we have those two quantum conferences that I mentioned. the workshop for quantum repeaters and networks. We restrict attendance to that to 100 people so that we can have a small conversation, but we can have twice that many people. And the QCrypt conference is 300 to 500 people, depending on the location. So there are a lot of people around the world who are already working on the technologies, and the goal is to bring them together with the people who really understand the way networks behave.
Because I think you need more, you need to enhance more people who are not so familiar with this area into this discussion. So that's why
Well, hopefully we've made a start today.
Thank
so
you.
we should go move on to our next talk. But thank you so much, Rod, and audience. Yeah, Matt.
Yeah, I just wanted to say I'm using the Etherpad for taking notes, so you might want to go in there if you asked a question and make sure I didn't butcher your name or butcher what you said.
Thank you.
Thank you. And the slides, Allison, PDF, which I assume will get uploaded. There are some references in there that I didn't talk about, but you can look up those references if you want to know more, or contact me and join the research and join the mailing list.
They are uploaded already, so so that people can do that. Okay, so thank you. That's great. Goodbye. I'm going to switch off, and we're going to introduce our next speaker now. We have the first of our ANRP presentations. You want to come up to here? Let me get your slides up here as well. Okay, hang on. And I think, hopefully, here. I'm sorry. Here. And they're unfortunate, so I don't know if I can make them large enough. Do you want to? Sorry? Did you get the latest version of this? Yeah, I think they are. Yep. This is the ones you gave me late in the night, but they are. I was thinking about making them larger, but I don't think we can. It's probably about as good as what I. Oh, most view. Here, this. Yes. Oh, there's a slideshow. I didn't know that. Okay. There you go. That's. I think. Maybe full screen will actually be better. Okay. Because this is just going to. Here, you play. Will you introduce yourself? Okay. Yeah. Yeah, I think you should be able to do that. See if it works. Oh, no. Okay. Here, we can put it near you. We can, just tell me what to change. I think it's not working. I may not have the right attachment for it. Yes. Oh, it's here. That's what. Okay. I'm so clueless. Sorry. That's okay. Okay. So that should work. Yep. Okay. That should. Yeah. Okay. All right. Introduce yourself.
Hi everyone, I'm Mojgan. I'm going to present to you our work on performance characterization of a commercial video streaming service. My current affiliation is with Akamai, but I did this work when I was a PhD student at Princeton and interning at Yahoo Research. So we all have had that experience that when we're watching our favorite video and there's a buffering and you end up wondering why. And even as the networking community, we often wonder what happened and what's the problem. And in this work, we have an unprecedented data set to, for the first time, instrument and study the entire end-to-end video delivery path. And with video being the dominant application of the internet, with making up more than 70% of the traffic, at least in North America during peak hours, it's particularly important for us, and we can uncover a wide range of problems for the first time with this data set because we have data from the entire path. So I'm going to walk you through a list of performance problems that we have found. I'm sorry.
Oh, you must have touched it, I guess, right? It changed when you didn't ask it to? Here we go. You want to be here?
It's showing 2 and 3 at the same time.
Oh, I see. Oops. No, that's not good. I don't know why. I see what you're saying. Oh, maybe we should just do full screen.
Okay.
I guess we should have practiced this. That's annoying.
Sorry. It's showing both slides.
It's doing more than one side at a time.
Yeah, I guess I can just click like this,
Well,
but
we
it
should
won't
be
be
able to
large,
get a
but we
better
can just
screen
enlarge it.
of yeah.
I think if you just enlarge it.
Oops, sorry.
No, it's just both.
Got it again.
I think it's fine.
Yeah.
Let's do it like that.
Okay. Oops.
Or not.
Sorry.
Okay, this is.
Okay. Oh, I don't think people will be able to see that well now. All right. Okay. How about that? Okay.
Okay, so here's the list of problems that we have found. Don't worry about reading this because we're going to be walking through this for the talk. So first, let me start by showing
We need
you.
research on projection systems, eh?
Yeah.
Yeah. Yes, we're on the Mac.
I can actually make it. Do you mind if I bring my laptop?
Okay, let's get her laptop on.
Yeah, that's fine.
Okay.
No, we just
Sure.
plug it into the HDMI.
Yeah.
You got an HDMI cord?
Should we have a research task force for the projectors and displays? Yeah, maybe by the time we have quantum, we'll be able to do it right. We'll have new ones. Quantum microphones.
I'm afraid that's an unsolvable research problem.
Yeah. You have the, I don't think it's the same dongle as this, though. Is it USB?
I do.
Oh, you have a HDMI directly, good. Okay. Yes. Okay, yeah, you get to restart your time. We're letting her restart her time, too.
It's okay, you can start.
Okay,
I also get this.
all right. Thank you for your patience, everybody.
Okay. All right, we're back in business. So here's the list of performance problems that we found, but don't worry about it. I'm going to walk you through this list through the talk. But before that, let's look at the system that we instrumented so you can get an idea of what could go wrong before we show you what did go wrong. So the system is Yahoo's video streaming system. And the way that streaming works, very high-level overview, it starts by the client, which is your player, requesting and receiving the manifest, and the manifest is the list of available bit rates. And then there's usually an adaptive bitrate algorithm on the player that chooses which bit rate to request for. And then once it decides the bit rate, it sends an HTTP request to the CDN to get that. And in this system, these HTTP requests are sharing the same TCP connection. And each chunk in this system is 6 seconds. Once these requests arrive at the CDN inspects its local cache. If it's there, it serves it to the player. If it's not there, it's called a cache miss. And you go to the backend to fetch the content first. Our CDNs in this system, the CDN servers are using Apache Traffic Server, which is a popular HTTP proxy. and the caching eviction policy is LRU. And then finally, when these chunks arrive at the client side, they have to pass the client's download and rendering stack before they can be shown to the user. And we will go into more details of what these mean later in the talk when we get to the client section. So our goal in this study is to identify performance problems that impact video QoE, and in particular make the users unhappy, so they will reduce your revenue. And if we have only data from the player side, for example, if you have QoE data, for example, the Convivo data set, you may be able to detect some of these problems. You may be able to say there was a rebuffering. But because of the buffer itself, some of the problems get masked because of the buffer, so you may not see an immediate impact on the QoE. And also, if you only have player-side information, you cannot detect problems that happen in the network or the CDN. And looking at it from the other side, from the perspective of if you have only data from the CDN, for example, server logs, you may be able to detect some of the problems, but you will not be able to isolate problems that are within the client's machine. So fortunately for us, we are looking at this from a content provider's point of view. For example, Yahoo or Google could do this. And what's unique about them is that they control both sides. So this is an in-house CDN and their own player. And once you have view into the entire path of the video delivery, then you can find problems everywhere and see exactly what happened for each chunk that you had rebuffering. So our approach relies on three principles. One is end-to-end instrumentation. We instrument both sides of this path, including the player and the CDN servers. And this is important for us to join this together to be able to construct the life of a chunk, what happened where. The instrumentation unit is per chunk because a chunk is a unit of decision-making in this system. For example, the bit rate that the adaptive bitrate algorithm chooses may change from chunk to chunk, but not within a chunk. And whether the file was a cache hit or miss at the CDN also may change in the granularity of a chunk. We did consider sub-chunk measurements. There are two reasons that we did not go with it. One is that it is too expensive, and this is a production player in CDN. This is not an experimental player or CDN. And once you start using too much CPU on the player, you can have a negative impact on the QoE, and the users may start seeing the frames may get dropped and things like that. But also going sub-chunk and doing sub-chunk measurements can sometimes be technology dependent because the way that HTML5 handles data arrival is different from Flash, and we wanted the results to be applicable to all internet video. And finally, collecting TCP statistics. The statistics that we are collecting here, they're sampled from the CDN host kernel. There are some limitations here as well. This is an operational and large-scale setting. So there's the frequency that we can collect this information is not high. So what do we mean by this end-to-end per chunk measurement? So the bold lines here are where we are measuring things directly, and the dashed lines are where we cannot instrument things directly. So the observation is based on inference. And the life of the chunk starts with player sending an HTTP GET request. It arrives at the CDN. The CDN has some processing time, and we show that with DCDN. If this was a cache miss and backend needs to be involved to get the first byte, then there's a backend latency. Everything that is not measured directly is shown with red, and everything that is measured directly in this instrumentation is shown with blue. And then finally, the first byte arrives at the player. The time difference between when the HTTP GET request was sent and when the first byte arrived is shown with DFB, first byte delay. And there is also the download stack latency shown with red, DEDS. And similarly, when you have the last byte of the chunk arriving, that's the time difference between the first and the last is shown with DLB, last byte delay. And this is important because this is going to come up for different kind of studies that we do. So before I show you our results, I want to point out that we are studying QoE factors individually in this talk. The factors that we choose, this is a very rich area of research, and they have shown that most important QoE factors that impact the user's experience are video startup time, rebuffering rate, video quality such as bit rate and frame rate. And we look at these factors individually instead of coming up with a QoE score because of two reasons. One is, depending on the type of content that you have, some of these factors may matter more than the others. For example, for a breaking news video, startup time matters more because the user just wants to see the news. Whereas when you're sitting to watch a long movie, the startup time may not matter that much, but video quality matters more. And second is the length of the video. Shorter videos, users are usually less patient, and you want to have the results. You want to start playing right away, whereas with a longer video, the user is already patient and they have it in their mind that they're going to sit and watch a 2-hour video. So this is the outline of the talk. We've already gone through the introduction. I'm going to show you the measurement data set that we have, and then what are the problems that we found in server side, network, or client side, and then we're going to conclude the talk with takeaways and what can be done about these problems. So the data set comes from Yahoo videos. They're played over a variety of sites, for example, news, sports, finance. And like I said, this is the real player that was used in a variety of sites. Our data set comes from 18 days. This is a video on demand data. 85 CDN servers across the US were instrumented, selected randomly. We studied 65 million video sessions and more than 500 million video chunks. The users are predominantly in North America, over 93%, and mostly non-mobile users that are not using proxy. We go into more details in the paper on how we remove users that we think are behind the proxy, and the main reason for that is we want the TCP measurements to reflect the path between the server and the client, and usually the proxies terminate the TCP connection, so it would make our results not accurate. In terms of the video streams distribution, this is a popular heavy workload with 66% of the requests arriving for the top 10% of the titles. And most of these videos are shorter than 100 seconds. So let's dive into the first category of problems, the server-side problems. So our measurement in the server side comes from direct measurement. So at the player, we have session ID, chunk ID, startup time, rebuffering, and video. And at the CDN, we have session ID, chunk ID similarly. We are measuring server latency, backend latency, and cache hit or miss. So because we have this data readily available, we can show, for example, the immediate impact of server latency on startup time. And there's no inference there, there's just ground truth. So for example, this is one graph that we can do because we have data from both sides, and we can show the impact of server latency on startup time. The x-axis on this graph is the server latency in milliseconds. The y-axis is the startup time of the video in seconds, and you can see how it significantly increases with higher server latency. So next, we are interested in knowing why do I have these servers with these high latency. The first issue that we found is the Apache traffic server retry timer and cache misses. So what happens when an HTTP request arrives at the CDN is that it first inspects the memory, and if it's not there, you go to the disk, and if it's not there, you go to backend. However, you don't want to overwhelm the backend, so when multiple requests come for the same content, there's usually a timer there that stops you from going to the next tier for a while to not overwhelm the backend. And we found this misconfiguration that was still true between the memory and the disk, and it was impacting about 65% of the chunks in our study. But even more important than that is cache misses. We found cache misses in this system increase the server latency significantly. The median increases by 40 times and average by 10 times when your server side has a cache miss. And we also found these extreme cases where server latency was worse than network. And for those sessions, they were often caused by cache misses. The average cache miss ratio in this data set is 2%. For the sessions that had worse server latency than network was 40%. So it is often caused by this significant impact of cache misses on the server latency. Another interesting thing that we found is that server-side problems are persistent. That means that once the session starts having server-side problems, it's persistent, it stays. And for example, like I said, the average cache miss ratio is 2%. If you look at the conditional probability of the sessions that had one cache miss, the cache miss ratio for those sessions goes up 60%. That means that cache misses are coming in groups. And that's usually because of the unpopularity of the title. So once a title is unpopular, its chunks are more likely to reside in disk or worse yet in the backend. And you start having cache misses, but every single one of these chunks are going to go through that. And in fact, we found an interesting paradox in this system that it seems like more heavily loaded servers seem to have lower latency. But this is the result of the cache focus mapping. Cache focus mapping is you're trying to have hot caches, so sending the request to where it was recently served from, which causes your popular content to go to the same servers, and your popular contents have better performance because of the reasons I just mentioned, but you also have more requests for your popular content. So there's this, there are these servers that are less, have less demand because they're serving unpopular content, but have worse performance. So the content popularity is even dominating the server load in this case. So the next category of problems are network performance problems. So we're all familiar with network problems that can manifest themselves in the shape of packet loss, reordering, high latency, variation of latency, and so on. And they can be transient or persistent. It's important to notice and separate these two from each other from the video QoE perspective, because video does have the adaptive algorithm that you may be able to adapt to some transient problems. But you can't avoid bad QoE forever when the problems are persistent. And the way to fix those is by CDNs or ISPs actually taking corrective actions, for example, fixing peering. So our network measurements come from us instrumenting our host kernel. So basically, the orange box here is showing what the operating system is doing, which is there's this TCP info struct, and OS is collecting this information about all the TCP connections, including the weighted average of RTTs, called smooth RTT or SRTT, congestion window, and packet retransmissions. And what we do is the blue box. That is, we pull this every 500 milliseconds per chunk and store it, and then later we use it across chunks and across sessions to see what happened in the network. Of course, there are some challenges in collecting data this way. We're looking at smooth averages of RTT or SRTTs instead of individual RTTs. And that's not sometimes a good idea, especially if you're dealing with these long connections for video streaming, because the SRTT is not reflecting your RTT during this chunk exactly, but what happened in all the previous chunks. This network snapshot frequency is also infrequent. 500 milliseconds in many cases is more than the RTT of the connection. But it comes from the operational limitations and how often we were allowed to pull this and how much data we were producing in terms of storage overhead. And finally, because this is an operational at scale, we can't collect packet traces. And in the paper, we go into more details in how we grapple with these challenges, but I'm just going to show you the interesting findings. So here's another similar graph that we can do because we know the network latency and, for example, the SRTT of the first chunk, and we also know the startup time. So if you look at the SRTT of the first chunk, that's the x-axis here, and the impact on the startup time of the video, the impact is visibly clear, and how there's a significant impact on the video startup time. So let's dig in here and see what causes this network latency to be so high. So to do this, we aggregated IP prefixes, the client IP prefixes, into /24, and we looked at the ones that are most recurring in the 90th percentile every day. So we're looking at the tail of a tail. And among those, we found 75% of them to be located far from our CDNs. So geographical distance or propagation delay is the main cause. But surprisingly, about 25% of them were located in the US, and majority of them were actually close to our CDNs. And we did further investigation, and we saw that there's also a high latency variation which is a little bit different from a high baseline. It's just a variation. And in both cases, we find that majority of these prefixes are in enterprise networks, not residential networks. And what we speculate is happening here is that these enterprise networks are running their middle boxes, which are causing high latency and high latency variation, despite the fact that they're so close to the CDNs. Now, of course, we do not have in-network data to confirm it. This is just a speculation of why we see this high latency only in enterprise networks and not residential ones. The second finding is the impact of packet losses. This graph is generally what we expect to see in terms of how retransmission rates or losses impact video QoE in terms of rebuffering rate. Generally, we see that higher loss rate indicates higher rebuffering rate, but that's not all. And in fact, we saw that the timing of the losses are more important than the amount of your loss rate. And this is important for us as a measurement community to be aware of the fact that a loss rate, measuring loss rate does not necessarily always correlate with QoE. And the location or the timing of the losses matter sometimes more. So in this graph, we're showing you the x-axis, the chunk ID 0 being the first chunk, and the y-axis is showing the percentage of chunks that had rebuffering, and the blue graphs are showing that amount. So what's the percentage of the chunks that had rebuffering? And it is higher for first chunk, and you may think because of the loss. So to take that into consideration, we calculated the green plots. So those are the conditional probability of percentage of chunks that had rebuffering given there was a loss at this chunk. And you can see that if there is loss, the percentage of the rebuffering goes higher for everyone, but it goes significantly higher for the first chunk. So this is because of the existence of a buffer in a video streaming session. So when you have a buffer in a video streaming session, initially it's not full, so it cannot hide these impacts from the user. But later on in the video streaming session, when you're on a higher chunk IDs, then there's enough buffer to hide some of these impacts from the users. So here's an example case. Here's a very extreme case. So here we're looking at two sessions. Red had rebuffering and green did not have rebuffering. And you're also looking at the distribution of the loss rates. This is retransmission rate in chunks. And you can see that the red session that had rebuffering has actually generally lower loss rate. And the green had significantly higher retransmission rates. But because they happened after the first 4 chunks, which is already buffering 24 seconds of video, because each chunk is 6 seconds, the user actually never finds out about it. Whereas the red session is very unlucky and has losses in the first chunk, and right there it has a rebuffering. So here's an example of how the location of the losses seem to be even better more than the loss rate. Unfortunately, we found earlier packet losses are also more common. So you saw they are more harmful, but they are also more common. This is because of the bursty nature of packet loss in the TCP slow start. But we'll talk about how some server-side pacing can help. With this graph is showing you. This graph is showing you the average retransmission rate per chunk ID. You can see this huge difference in chunk ID 0 versus others. And finally, we found throughput to be a bigger problem than latency for video streaming. So here we have defined a performance score, which is a chunk duration. In our case, it's 6 seconds, divided by first byte plus last byte. And the first byte is a measure of latency. If you remember from this graph, first byte was the time difference between when the HTTP GET request was sent and when the first byte arrived. So it includes the network latency and the CDN latency, and if you have backend, if you have a cache miss, also backend latency. And the last byte delay is basically a measure of throughput because it's a difference between the first and the last byte of this video. So we have divided the chunks in our data set into 2 sets based on if this performance score is more than 1 or less than 1. When the score is more than 1, that means more than 1 second of video is delivered per second to this player. And from very simple queuing algorithms, if you have more than 1 second of video delivered to your player, but the user is watching 1 second of video per second, you're going to build up buffer. And when the score is less than 1, that means less than 1 second of video is delivered to your buffer. Your user is still watching 1 second of video per second, and that means you're depleting the buffer. You're expected to have rebuffering at some point. So once we divided our chunks into these two sets, we found that the contribution of the last byte delay in the bad chunks was orders of magnitude higher than latency. And this shows to us that throughput seems to be having a bigger contribution in these chunks that do not arrive in time. Third category of problems are within the client. So what is the client download stack? When the chunks arrive from the network and before they are delivered to our player, they go through the download stack at the client, which is the NIC, the OS, and the browser before they're finally handed over to the player. And unfortunately for us at scale, we cannot observe the download stack latency directly. Because we can't go and instrument these clients and see what's happening at their browser or network card. So here we're relying on detecting outliers. So here we're doing some statistical work to see if there is a chunk that seems to have been buffered at the download stack. So if a chunk has been buffered at the download stack, I expect it to be delivered late to the player. And that means that I'm expecting the first byte to be significantly higher than others. So let's say it's 2 sigma away from my mean. But also because it was buffered at the download stack and delivered so late to the player, I expect it to be arriving at the machine's throughput, not at the connection's throughput. So it's going to have a very high instantaneous throughput from the perspective of the player. So let's say it's 2 sigma away from the mean again. But this should not have been caused by network and server, so it should have similar network and server performance. So here's one example that we found in our data set. The graph on the top shows you the latency metrics, and look at chunk ID 7. And you can see that it has similar RTT and server metrics, server latency, but it has a significantly higher first byte delay than the rest of the chunks. So what we expect is happening here is that this chunk was buffered at the client download stack and delivered late to the player. And then the throughput measurements are at the bottom. You can see the blue line is connection throughput. And we know the connection throughput because we know the congestion window in RTT. And the red line is showing the download throughput from the perspective of the player. And you can see that the same chunk seems to have a significantly higher instantaneous throughput, almost 4 times more, which is not possible in this connection because we are measuring this. So it's important to be aware of these problems that we can only find with once we have data from both sides, because if we don't have this, each side is going to blame the network or the other for these problems. And this can be very dangerous in the video streaming world, because if your player makes incorrect assumptions about, for example, latency from the first graph, and if the adaptive bitrate algorithm is latency sensitive, it can cause undershooting because it may freak out and think the latency had a spike, where in reality it didn't. Or if your player is sensitive to throughput and it's using the lower graph, then it may think the world is so much better than it actually is, and it can cause overshooting in the adaptive bitrate algorithm. So it's important for the player to have some view into the network path that in our system the player didn't, because we only had these TCP measurements at the server. So we found these download stack problems, the transient problems that I just described to you. We found them to be more common in the first chunk. And in the paper, we go into more details of how this could be a possible side effect of flash. And we also have persistent download stack problems. The persistent download stack problems are not very common, but what's important about them is once they happen, they often are the most important factor, and they are higher than network and server latency. And there's more in-depth conversation about them in the paper if you're interested in that. And finally, the last category of problems are the rendering stack performance problems. So what is rendering stack? So the chunks have finally arrived at the player, but they're not ready to be shown on the screen yet. And here we have a rendering stack. These chunks need to be demuxed, meaning the audio should be separated from the video, and then they have to be decoded and finally rendered. And this can be done by CPU or GPU. If it is done by GPU, it's called hardware rendering. If it's done by CPU, it's called software rendering. Now, if the CPU is busy and you're using software rendering, the quality may drop, which causes high frame drops. But also, if your video tab is not visible, your browsers do optimizations to reduce your CPU consumption, so they intentionally drop frames. So to detect these problems, but to separate them from browser optimizations, we have introduced Boolean variable viz, is this player visible or not? And also we're measuring the drop frames. And then for each session, we are also collecting what OS and browser has. And there are some interesting findings here. First one is that good rendering is actually time consuming. We found that demultiplexing, decoding, and rendering takes time, and you have to provision for that if you want to have a good frame rate. And so in this graph, we're showing you the download rate of the chunk, the average download rate of the chunk, and the x-axis, and what's the percentage of the drop frames. And you can see the drop up to about 1.5 seconds per second. And that's what we recommend to use as a rule of thumb, at least in this system, for avoiding having higher drop frames. Next, we found kind of a paradox again, higher bit rates showing better rendering. So higher bit rates put more load on CPU, and as I explained to you, software rendering can be expensive. So we were expecting them to have worse frame rate, but we actually see them having better rendering frame rate. And we did further investigation. You can see the numbers in the paper, but in summary, we found these higher bit rates coming from connections that had lower RTT variation and lower retransmission rate. So they were often requested in better conditions, and as a result, they were able to provide the 1.5 seconds per second rule more often and had a lot of extra time to process this, and the impact was hidden from the user. And finally, we found some very unpopular browsers that had a really bad rendering. So here we're looking at chunks that had already good performance. So the rate, the arrival rate is more than 1.5 seconds per second. And we know the player is visible because we're filtering on only the chunks that have visibility, so the user is actually watching. And we divided the chunks into two major platforms, Windows and Mac, and these blue bars are just showing you the percentage of the chunks in each platform for each browser. And they're sorted from more popular to least popular. And here you're looking at the percentage of the drop frames in each of these browser OS combinations. You can see the trend is the opposite. And we found, so in the paper, we further break down the other category, which are the least popular in each one of them. And there are some interesting cases there that have really bad rendering, despite the fact that we have made sure the arrival rate is good and everything else is similar. One of the interesting examples are Safari is actually really good on Mac, but it's among one of the worst on Windows. And on Windows other section, there's some less popular browsers like Yandex and SeaMonkey that we found that had huge problems in terms of rendering. So I walked you through all these problems, but let's see what are the takeaways and what can we do about all of these problems at each one of these places. So let's start with the CDN. I discussed 3 problems with you about the CDN. One is the impact of cache misses. So in this workload, we're looking at popular heavy workloads. And I told you we are using the LRU cache eviction policy. Because of the impact of cache misses that are so high and the workload is popular heavy, we propose using other policies that are more tuned for these kind of workloads like GD size or perfect LFU. In terms of the cache miss persistence, we propose prefetching subsequent chunks. This is the problem that I discussed with you, that once the session starts having cache misses, every one of its chunks is going to have the cache misses because it was most likely an unpopular title. Now, it's not that simple to just prefetch the subsequent chunks, because in many cases, the CDN does not know what bitrate is going to be requested in the next chunk. But that's a whole other area of research. We could talk more about it if you're interested. For the low latency paradox that I explained to you, we propose better load balancing by partitioning the popular content. If you remember, 66% of the load was for the top 10%. So even if you balance that better, you can get better utilization of the servers. The network category of problems. I discussed 4 problems with you. There are more takeaways and problems in the paper if you're interested. But the first problem was we found some nearby clients with high latency. It's important to know this even as a CDN because sometimes you want to know what you can do, but sometimes you should be aware of what you shouldn't do. So in this case, you should avoid over-provisioning servers for these nearby clients because the problem is not that they're far from your points of presence. And in case of prefixes that have persistent high latency or variation, as a content provider, the options are limited of what they can do about this problem, but the least that you can do is to adjust the adaptive bitrate algorithm accordingly. For example, you can start with a more conservative bitrate or increase the buffer size to handle these latency variations better. In terms of the earlier packet losses that are more harmful and unfortunately more common, I discussed using server-side pacing. And finally, the throughput is a major bottleneck. We think that's actually good news for ISPs because it's easier to fix by establishing better peering points than latency. The takeaways on the client, I discussed the download stack latency problem with you. And we think that's an important problem that we could only find it because we had data from both sides. And we could confirm that this problem is not being caused by the server or the network. And I talked about how that can be dangerous for the adaptive bitrate algorithm. It can cause overshooting or undershooting. And what we propose here is incorporating some server-side TCP metrics or some awareness of the network path to the player. And I had these discussions with the path-aware networking folks yesterday. And the second problem is that rendering is resource heavy, so you should provision for that. We propose using 1.5 second per second video arrival rate as a rule of thumb. This is particularly important if you are streaming videos that people care about frame rate. For example, sports, that there's usually that one frame that has whether or not it was a foul. And finally, rendering quality differs based on OS and browser. And I showed you some example browsers that even in good conditions and similar network and server conditions, they seem to have worse rendering quality. It's important for a content provider to know this to avoid premature optimizations. For example, rerouting this client while the problem was at the client's own download stack is not helpful. So it helps CDNs and ISPs to know when the problem is the client to avoid premature optimizations there. So in conclusion, in this work, we instrumented both sides for the first time, the client and the CDN server, and it allowed us to uncover a wide range of problems for the first time. We have data per chunk and per session, which allows us to uncover whether problems were persistent or transient, and whether they lasted throughout the life of this video streaming session or not. And our findings were used to enhance performance in Yahoo. And with that, I am happy to take questions.
We'll take about 5 minutes of questions, maybe more.
Hi, my name's Stuart Cheshire from Apple. Thank you for a really interesting presentation. As you said, most of the traffic on the internet today is streaming video, so it's clearly something people care about. And I think we're all frustrated by seeing that little spinny wheel waiting for it buffering. I had one comment. You talked about client download stack latencies, and working for Apple, that's the area of this that
Right.
I'm more involved with. I think I may know what's going on here, so let me...
You're talking about this, right? The other section in the Windows?
Oh, well, no, I was happy to see Safari scores best, so thank you for
On
that.
Mac.
No, you were talking about in the pipeline, the various delays in the CDN, the network, and when you're talking about the client-side download stack,
Right.
as far as I know, there is no networking API on Windows or Linux or Mac that will just sit on data for no reason and not deliver it. I think this is a consequence of the API's in-order delivery of data.
Yes.
That if you miss In a common network setup now, unfortunately, we have lots of buffer bloat, so you could easily have a 2-second queue on your cable modem link, and you lose one packet, and fast retransmit fills in that one packet really fast, but it's at the back of a 2-second queue. So you've got all this data arriving, piling up in the kernel, the sockets API can't deliver it,
Yes.
and then the one missing packet arrives, and it says, here you go, here's 200K all at once. And of course, that looks like this blip that you've had zero throughput for a couple of seconds, and then suddenly 200K delivered in 0 nanoseconds is infinity throughput instantaneously. So we have definitely seen that with things like the Apple TV product, that we get plateaus of no data at all, and then suddenly a spike where it apparently all arrives because the one missing packet got there.
Yes, I completely agree with you. Actually, we have more data in the paper that we confirm what you're saying, because we collected like timestamps at the NIC and we collected timestamps at the browser, and it's usually the API. The problem here is that our player is sitting on a black box.
Right.
And we can't, it's probably the way that they're handling, like there's a buffer there, and how they're handling the data delivery that causes these problems. But because it's a black box and it's like a footnote in the paper that we can only guess this is what's happening, and we confirm it is not at the OS for the browser. It seems to be there, but we can't really measure what they're doing in that API.
I think you have a good point there. With the current APIs, you can't tell if there is just no data or if there's lots of data with one missing packet. Right?
Exactly.
Yeah, that's a good point.
Wes Hardiker, USC ISI. Excellent presentation and work, very thorough, and I really enjoyed it. Having said that, you killed my dream. And I've had this dream that with the advent of, users can go out and find the things that they want, and they'd help us discover new things. Unfortunately, sort of your caching results kind of indicate that video streaming services are, it's in their desire to bin everybody into popular titles, where they won't give you as many suggestions sideways of other things that you're interested in. They're more likely to give you suggestions that everybody else is going to watch too, because it's cheaper for them, gives them better performance, and thus better ratings, and that's sad. But thank you.
That's true, and I think everybody does that.
Hi, this is Zihao. I just wondered whether the system is intended for VOD or live streaming or both. Thank you.
So the data set that we use here are from the video on demand, the data set that I discussed. But the same systems are used, like the same CDN, and the configurations that we found, they were applicable to the live streaming events as well.
Okay, thank you.
This is from the Jabber Room. Simon Pietro Romano asks if I'd be curious to understand whether all of this has been carried out with Flash-based clients. In such a case, is there any updated study with MPEG-Dash?
Yes, I think we mentioned that in the paper.
Okay.
The codec, yeah.
Okay, thank you.
Okay, well, let's thank Jen. Okay, I'll reassemble for last fall. Okay, coming up. Do you want to try using your own machine? That's probably safer. We're quick enough.
Challenge accepted.
Yeah, really. Oh, this is yours. Here we go. All right, change of topic, but not really change of area, so you want to put that in. Here's your clicker. All these nice new Macs. Okay, oh, signal. Oh, looking better. Yes, okay. Okay, so introduce yourself. So this is our second ANRP speaker.
Hello, hello. Everyone good? Cool. Okay, so good morning, everyone. My name is Vaspo. I'm a third-year PhD student at the University of Michigan, Ann Arbor. This work is originally appeared in ACM SIGCOMM 2017, last August. So today I will be presenting Vroom, a new solution to optimize web performance. This work is a collaboration with Ravi, Muhammad, and my advisor, Harsha. So let's get started. So as you have experience, using a mobile phone connected to a cellular network is very, very common nowadays, right? We have all used phones to surf the web all the time. Now, a study has shown that this is in fact the case. Mobile web usage has been increasing over the past few years. The year 2016 was the tipping point where mobile web usage has surpassed desktop devices usage to browse the web. But despite all of this increase in mobile web usage, as you may experience yourself, loading many of these pages are actually pretty slow. Keynote Systems found that it takes almost 10 seconds to load the median mobile retail site. And on the other hand, DoubleClick found that it takes 14 seconds on average to load a page over a 4G connection. So we also confirmed this ourselves using a Nexus 6 phone, a reasonable high-performance phone at the time, connected to a good LTE network in the Ann Arbor area to load the mobile-optimized popular pages. So one thing to note about the results that we found here is that these are heavily optimized popular pages. So the numbers that we get here is on the better side of things. So this is a bar chart representing the page load times measured in seconds of the Alexa top 100 sites overall and the Alexa top 50 news and 50 sports sites. The top of the bar chart is the median page load time, and the whiskers are 75th and the 25th percentiles. At the median page load time for the Alexa top 100 sites overall, it takes 5 seconds to load the median page. This is actually pretty slow, considering the fact that some studies have shown that 5-second page load times has 25% bounce rate, which means that these pages are actually losing some money, right? And on the other hand, if we take a look at the Alexa top 50 news and 50 sports sites, things are far worse. The median page load time in this case is actually 10 seconds. And the reason why things are much worse in this case is because news and sports sites tend to be more complex than the Alexa top 100 sites overall. So in this talk, I will be first digging into why web pages are slow to gain some intuition as to why that's the case, and then we will use those intuition to improve web performance. Then I'll use the intuition that we get from the first phase to explore Vroom, our solution to make web page load faster. And the last part would be the implication of our work, Vroom. Now, let me take you into why web pages are slow. Now, let's take a very simple example. Let's say we want to load a page from a.com, and this a.com contains only one image. So what would happen when this page gets loaded is the client will send a GET request to a.com. A.com sends back a response, client parses it, discover the image, and then it fetches the image. If we take a look at the network utilization and also the CPU utilization at the client, as you can see here, the bars with the solid colors are times when these resources are being actively used. And as you can see here, there are no periods that the CPU and the network is being fully utilized. And the crux of the problem here is that the client has to parse or execute a resource to discover additional resource to fetch. So in some instances, CPU will get blocked by the network, waiting for a resource to arrive so that it can start parsing. And on the other hand, sometimes the network will be idle because it needs to fetch, because it's waiting for the CPU to process some resource. So the idea that we want to make page load faster is by making either the CPU or the network to become fully utilized. But before we jumping into how we can do that, we first have to understand whether the CPU or the network is the main bottleneck here. So what we did was we conducted an experiment to find the page load times when either the CPU or the network is the main bottleneck. In order to find the page load time when the CPU is the main bottleneck, we use the phone connected to a wired network so that we have a near zero latency and also almost like an infinite bandwidth. And on the other hand, if we want to find the page load times for when the network is the main bottleneck, we remove any processing from the page load process. And as you can see here from the results, the page load times when the CPU is the main bottleneck is actually much higher than the page load time when the network is the main bottleneck. So in this case, the median page load time is 5 seconds in the case where the CPU is the main bottleneck. So that experiment implies that CPU is the main bottleneck in most of the cases. But is this actually the case everywhere? Sure, there may be cases where network can be the main bottleneck. For example, a developing country where they have 3G connection, a much slower connection than 4G. Sure, network can be the main bottleneck in that case. Or on the other end of the spectrum, if you're using a flagship phone, maybe your phone is much faster than the network, so the network is the main bottleneck. But if you consider the technology trend, network is getting faster and faster every year, right? Network will have higher bandwidth and also lower latency. But on the other hand, CPU is only increasing in the number of cores. The clock speed itself is not increasing. But how is this trend affecting page load times? So what we did was we also performed the same experiment, but instead of using all cores in the page load time when the CPU is the main bottleneck, we disable one of the cores to see what is the effect of this. And what we found was that by disabling one of the cores, the distribution of the page load times when the CPU is the main bottleneck is very similar to when using all the cores. And this actually stems from the fact that browser processing is largely serial. There's one main process that keeps doing everything. There's not much leverage in multiple cores. So the implication here is that the CPU will become the main bottleneck in the long run. So just to recap what we found in this first section of the talk. So the reason why web pages are slow right now is browsers need to discover resources from parsing and execution. And we know that browsers are largely serial in discovering these resources and performing the page load. And with the CPU becoming the main bottleneck in the future, this process of discovering resources from parsing and execution will not become any faster. So we have to somehow rethink the way page load should work. So our main idea in our project is to somehow have the server to become more proactive during the page load. We want servers to aid clients in discovering resources during the page load. And that's the main theme of Vroom. So now that we know why web pages are slow and gain some intuition as to how we can make web pages faster, let me walk you through Vroom, our solution that uses that intuition to make web page load faster. This is a very high-level architecture of Vroom. So we have a client, a mobile client, a web browser unmodified. And we also have these web servers, like what we used to have like right now. The client can start by sending a GET request to foo.com. Foo.com sends back a HG response. None of these are modified. Everything is the same as the status quo right now. But instead of only sending back HTTP response, Vroom also used HTTP to push resources down to the client so that client can receive many resources before it needs to actually discover them from parsing or execution. But push itself is not really enough because HTTP push only allows you to push down resources that the origin owns, right? So, but we know that a lot of these pages contain third-party resources. So we are missing out on a lot of resources to make web page load faster. So what we also include, in addition to HTTP to push, is also use some kind of dependency hints, resource hints. One way to do this resource hints is to use link rel preload, HTTP primitive, where the client will see this link rel preload. It can start the fetch of that resource as soon as possible. Now, in order for the servers to push or send these hints back to the client, the server has to have some kind of module to discover these resources, right? So we have these dependency resolution module running at the web servers. So these dependency resolution modules are just simply trying to find resources that the client will need during the page load. And at the client, we have some kind of scheduling mechanism so that the client can use all these resources as effectively as possible. Now that we know an end-to-end workflow of Vroom, in order to make Vroom a reality, we have to answer these two main questions. So first, how web servers can discover dependencies in the first place. And on the other hand, how clients can schedule these fetches of resources or use these hints from the server effectively so that it maximizes the benefit that it should receive. So let's first turn our attention to the web server. Let's consider this straw man approach in discovering resources for the client. So the client can send a GET request to the origin, right? This web server, foo.com, can start a page load of foo.com itself at the web server. Now, because foo.com's web server is a server, it has a much more powerful CPU and also a highly connected network. So it can perform this page load much, much faster than the client. So what foo.com can do is it sends back the response as well as push everything and also give hints on everything that it discovered during this page load. All of this sounds pretty intuitive and hopefully it works. Unfortunately, it doesn't. So there are two drawbacks with this approach. First, as we all know, web pages by nature is very dynamic. There are a lot of resources that is dynamically generated with some randomized token in the URL and so on. So by using everything from one particular load and hint them to the client or push them to the client, it means that we are pushing or hinting something that the user will not use. And by that, we are first going to waste client's bandwidth. Next, even worse, is that by having the client fetching these resources, we might be delaying some important resources, which make the page load slower in some cases. Now, on the other hand, as we all know, many of these pages contain many personalized resources. So in order for foo.com, in this case, to correctly account for personalization, it needs to get a hold of the client's cookie, third-party cookies. But foo.com doesn't have that. So foo.com will never be able to correctly account for third-party personalization. So how can we overcome these two drawbacks? So what we did was we used an intersection of offline loads to overcome the flux in URLs. So at the web server, we load a page periodically and then take the intersection of these loads So it means that anything that is randomly generated per load will be filtered out because of the intersection. But this is not enough. What we found was that by only doing this intersection of offline loads, we are only able to discover 70% of resources that can be discovered. So what we did was we augment online parsing of the HTML on top of intersection of offline loads. And what we found was that using these two combined online and offline resource discovery, we were able to discover most of the resources. So now that we have a way to discover resources at the web servers, let's turn our attention to the client and see how the client can effectively use these resources from the server. So let me walk you through the very high-level architecture of Vroom again. So Vroom sends a GET request to the web server. Web server sends back the response with the HTTP2 push and also dependency hints. It uses the dependency resolution module to push and to get resources to push and also hints. So one approach for this scheduling would be have the web server just push everything that it could from the dependency resolution module. And then for hints, just use our link preload, link rel preload to hint all of them. So what essentially this does is the server will push all the bytes that it could to the client, and the client will fetch all hints immediately at the beginning of page load. This sounds great as well because we are discovering resources much earlier in the page load, and things should work well. Unfortunately, it doesn't work well either. And this is a pretty serious problem because by pushing and fetching everything in the first place at the beginning of the page load, this leads to contention in bandwidth. And when there's a contention in bandwidth, sometimes the important resources are actually being delayed. For example, a blocking script or some CSS will get delayed. And because of those resources getting delayed, it has a cascading effect throughout the page load, and it can end up hurting the page load process. So what we found in our experiment was that by using this approach, we don't see any page load time improvements, and even worse, sometimes we see degradation in page load times. So what we did instead is we prioritized pushes and fetches of resources that can potentially have children. For example, HTML, CSS, or JavaScript. And one very important detail here is that we have to schedule them or hint them based on the schedule that they will be processed. We don't want to fetch any resources out of order so that, because if we fetch things out of order, some resource that gets processed earlier might stuck waiting after some resources that gets processed later. So now let's take a look at how Vroom Scheduler works in action. So at the beginning of the page, Scheduler fetches all HTML, JavaScript, CSS. This can both be in the form of HTTP2 push or link preload. After all of this fetches is done, it will start fetching other hinted dependencies, such as images, fonts. In other words, resources that will not have any children and that doesn't require any processing. While these two fetches are going on, we also allow the browser to parse the HTML, CSS, and also execute a JavaScript. If it discovers any resources by processing these resources, we also allow them to go out. Now this red line in the timeline is a very important time in the page load process. This red line is the time when all the bytes that needs to be processed at the client is actually local at the client already. So what this means is that from that point on, when the client wants to process any resource, it can start processing that resource without having to wait on the network. And from that point on, this implies that the CPU can be fully utilized. So now that we have the two components of Room, let me sum up Room, and then we can see how well Room works compared to the current state of the page load. So Room starts by sending a GET request to the origin. Origin sends back the HTTP response, pushes important resources, and also provide hints of other resources. Room has these dependency resolution module, and also we use combined offline and online resource discovery. On the client side, we have the scheduler, which we schedule them by prioritizing pushes and fetches of HTML, CSS, and JavaScript. So now that we have an end-to-end working components of Room, let's see how well Room works. So what we found was that Room's dependency resolution is actually very accurate. And because of this, Room was able to speed up page load in many of the cases. We have a couple of results in our paper, but today I'll only be talking about how well Room works over the status quo. If you're interested in other results, please refer to the paper. Before jumping into any numbers, let me first tell you how we evaluate Room. So we use the Nexus 6 phone connected to a 4G LTE network to a web record and replay environment. So the reason why we need a web record and replay environment is because Room requires server-side changes. So ideally, we want to use a live experiment, but unfortunately, getting adoption of all this would be very, very challenging. Now that we know how we evaluate Room, let's take a look at the numbers. So using that evaluation setup, we evaluate Room on the Alexa Top 50 News and 50 Sports sites. And this is the bar chart representing the page load times measured in seconds as well. The top of the bars are the medians, and also the whiskers are 75th and 25th percentile page load times. The status quo load is, for this set of pages, is 10 seconds, like we saw earlier. So when we enable HTTP2 on all domains, we saw that by only doing that, we are able to take the median page load time down to 7.5 seconds. But if we enable Room at all domains, we are actually getting doubled of that improvement in page load times. And right now, the median page load times is actually 5 seconds, down from 10 seconds. And this is in fact very, very close to the lower bound, where we define the lower bound page load times as when the page is either network bounded or CPU bounded. Now, as we all know, onload event is not the ideal metric to use to get user experience, right? So we also evaluate Room on visual metric. So if we evaluate Room on the above the fold time, which is the time where all the objects appear on the screen. And this is the bar chart representing the above the fold time measured in seconds. So the status quo load takes 12 seconds to load at the median site. And when we used Room, Room was able to improve the page, the above the fold time from 12 seconds to 8 seconds. So that's a 4-second improvement in above the fold time. So now, one assumption that we made in all of our evaluations so far is that we assume that everyone adopts Room. But as we all know, adoption is challenging. So what we did as well is we evaluate Room when Room is incrementally deployed. So in this example here, Room is enabled at all the domains, right? So what we did was we consider first-party domains. So when I say first-party domains, let's say we are ESPN.com. ESPN.com also owns ESPNCDN.com, right? So we also consider ESPNCDN.com also part of the first party domains, because we assume that if they are going to, if say ESPN are going to deploy Vroom, they might as well deploy Vroom everywhere on their domains. So what we found in this setting is that most of the benefits that we saw in the case where we enable Vroom everywhere is actually still achievable from only enabling Vroom at the first-party domains. And that means that we actually don't need full adoption to make web page load faster. So now that we know how Vroom works and how well it works, let's turn our attention to the implication of Vroom. So Vroom leverages HTTP2 push and also link rel preload to enable server-side aided resource discovery, right? Currently, if a website wants to use any of these, it needs the knowledge of the developer to manually add H2 push or link preload into the responses. But Vroom shows that there's actually a systematic way, an automated way, that you can actually include these pushes and hints into the response. But that actually comes at a cost. If you recall, Vroom requires offline dependency discovery to construct a stable set of resources. This actually consumes a lot of CPU cycles and network at the servers. Imagine if you have thousands of pages running, serving at your web server. By doing periodic loads of these pages will be a huge pain. So what we think that we could do is maybe the client can help the server discovering these offline dependency resolution. So maybe we can crowdsource all these URLs during the page load that the client sees and then send it back to the browser. You may be thinking right now that maybe this is violating some privacy issues. So let's take an example. So this is a dependency tree of a website. In a very naive implementation, you can send all these resources as a list back to a.com. But this is obviously not good because let's take a look at c.com/ad.html. So that is an ad. So anything below that can be personalized or targeted to the user. So sending all of this to a.com means that we are giving up privacy of the user. So what we could do instead is sending everything in this green encapsulation. And this is in fact enough for a.com to discover offline dependency resolution. Because a.com, if you recall from the strawman dependency resolution, a.com cannot discover personalized resources correctly anyway. So by sending everything in this green encapsulation is actually enough. And then anything below c.com can actually be sent to just c.com. And this is also not violating privacy because c.com is the one serving the ad, so sending it back to c.com would be fine. Another very important lesson that we found in Vroom is that when doing these pushes and fetches of dependencies using link rel preload, we shouldn't be fetching all these resources at the same time. As we saw that if we do this, we don't see improvement in page load times, and worse, we are seeing degradation, right? So just to recap, what we did in Vroom was we grouped dependencies in different priorities. So higher priorities are resources that require processing. And then we perform fetches of these resources based on their priorities. So maybe one branch that we could do regarding these prioritization of preloads is that include some kind of priority to the link rel preload. so that the browser knows that, oh, this preload is actually higher priority than some other preload, so that the browser can schedule the load of these resources better. In fact, this is on a draft already in the W3C community, so I hope to be discussing this more with them. But just to recap, I think that having a priority would be a great addition. So to conclude my talk, I presented Vroom, an end-to-end solution that fully utilizes either the CPU or the network. Vroom was able to do this by decoupling dependency discovery from parsing and execution, by leveraging the server to aiding dependency discovery at the client. Because of this, Vroom was able to decrease the median page load times by 5 seconds for the popular pages. And with that, I'm happy to answer any questions.
Hi. Alex Mayhofer. Thanks for the interesting presentation. It's really nice to see that someone actually tries that out in practice rather than just looking at the standardization of it. I have a question. Do you employ any mechanism that you avoid pushing the same resource twice to the same client? I'm not talking about link preload, because the client would decide whether he has that resource already. Mm-hmm. But if you like push the CSS on each and every page, that sounds wasteful, or are there any technologies employed?
You mean having push, like say, A to CSS twice in the same page load?
So the user loads the home page, gets the CSS pushed, then he clicks on the subpage, he gets the CSS pushed again. Uh-huh. Are you doing anything against that, or?
In this work, I am not doing anything to prevent that, because we have control of all what we push, so we ensure that we're not pushing it twice. Does that answer your question?
Yeah, okay.
Can you give us a little bit of an idea on these sites which have been optimized for mobile? How many URLs are in a page, and how many of those URLs actually change the page and are not just spyware?
So
I know the figures for regular web pages, and it's tremendous numbers of URLs. I just don't know if people who are optimizing for mobile are actually giving up some of this overhead, which was always understood to be, people basically were designing web pages thinking that CPU and network is unlimited, and that's not the case for mobile.
Right. So your question is, for these set of sites that I'm looking at.
Yeah, for the LSM 100, yeah.
What are the, like say, the number of resources on the page and something?
Are we talking about hundreds of URLs or dozens or just?
Yeah, so what I found in these set of sites, at least the number of URLs that I found for these set of sites are at least 50 for sure. For news and sports sites, it's in the order of hundreds. So, yes.
Right, which means that actually if the people serving these sites really thought of their user and what the experience would be, they could cut down on this and maybe you wouldn't need your solution as much. I'm not saying your solution is not a great idea, but if people, instead of trying to force down our throats lots of advertising and spyware, actually thought of the customer and his quality of experience, they could solve this problem without needing more technology.
Right, yes, I agree.
So, Chen Cao from Huawei. Thank you for your talk and very interesting work. And in your dataset, my question is, in your dataset, do you have any data reflecting how many websites use the domain sharing technologies?
Using what? Sorry, I couldn't.
Domain sharing.
Domain sharding.
Yeah, domain sharding.
Okay. So, number of sites that are using domain sharding. Most of them are using domain sharding at the time that we performed these experiments. Hopefully that is less common if we move to HP2, but when I was doing this project like a year or two ago, I still see that this is common.
Okay, because your insight is that the CPU and either the CPU or network is underutilized, but using domain sharing, it's kind of a parallelism, and you can make better use of a CPU, either CPU or network, right?
Well, I think that's a separate issue, right? How browsers are actually designed right now is that there's one main process that is doing all these tasks. Sure, you can have another process that can do like preload scanning, but that's separate. But the main thing that is happening is in one process. So by having that only one process, you are able to only execute or doing something, waiting on the network on only one process. So sometimes sometimes the browser will have to wait for some processing to happen in order to utilize the network later in the page load anyway. So domain sharding will not help in that case.
Okay, thank you.
Hi. Your advice, I'm participating in the priority hints work that you mentioned. I think it would be extremely interesting to integrate the concept of the JavaScript scheduler into the browser's resource scheduling process. And in that context, the red line you showed where which separated the critical resources from the non-critical ones. Do you think there's a way from the browser's perspective to determine that in a deterministic way that doesn't introduce a gap? So trigger those non-critical loads in the ideal time seems like a complex problem. How did you solve that?
I don't think I have a good answer to that off the top of my head. And the reason is because, like you said, it's very tricky because even though we say that Room's resource discovery is very accurate, we are not claiming that we can detect all resources. Many of resources that, say, a JavaScript that has some kind of randomized token, we still can't discover those. So so from a browser's perspective, I think it's going to be really tricky to say that, oh, these are all the resources that it will need to process, and then it.
Yeah, I'm sure we'll still need processing, but just the part that I'm interested in is in determining in real time, determining the red line, determining the fact that everything critical or most critical things finished loading and we can start loading the non-critical ones. Like defining that red line would be extremely interesting.
Yeah, I agree.
Okay, thanks.
Yep, thanks.
Hi, Alan Chalik. I had a couple of thoughts, one of which is, did you do any research into seeing how many unnecessary resources actually were downloaded, that you had pushed something in advance and then it turned out that the browser didn't need it? I mean, one obvious example would be high DPI graphics, where the browser is deciding which resolution to download.
Unfortunately, I didn't do any study on that, like what are the resources that are pushed and not being used. So one thing to note here is that all of our experiments start from the assumption that none of these sites are actually doing any push or anything like that. So what we did in our work was that, say, if in the best scenario, if we try to push everything that we know of, and then will be used in the page load, and also hint everything without having out the worry of unusing, what will be the best case that we could get?
I mean, I guess another way to ask the question is, how many additional bytes were downloaded using Vroom than would have been downloaded if the page had just been loaded normally?
There shouldn't be more bytes, right? So sure.
Well, there's certainly some more bytes in the signaling.
So there will be more bytes in, like, say, the hints and those stuff.
Yeah.
So I don't know the exact answer to that, but I would think that it should be relatively low compared to the whole size of the HTML or the page.
Okay. And another thing that just comes to mind is this seems like a way if we had a better way to organize our HTML and JavaScript in the first place so that the browser could identify the critical resources earlier in the parsing, then perhaps this server-side trickery wouldn't be necessary. But now I'm tilting at windmills, so I'll leave you.
Thanks.
Matt Mathis, I sort of had a continuation of that thought. It feels like this is very good work and very cool stuff, but it feels like you're optimizing at the wrong layer in the sense that the content providers should be optimizing better ahead of time, and they're not for some reason. And I was wondering if you had any speculation about some of the incentives for it. Things like domain sharding, for instance, feels to me as an example of a technology that works the same way that excessive choice in a grocery store works. It has the effect of crowding out competitors because you can provide 14 different flavors of chips to use 14 times as much shelf space. And what this means is that somehow underlying, some of the people have inappropriate incentives, and you're optimizing away some of their incentives, but the real problem is they're optimizing against you. Did you look at any of the sort of the causes of why this stuff was done in ways that that you could fix it in the post-processing, so to speak?
So just to rephrase your question. So basically, so what I'm optimizing is actually maybe we should be optimizing at a different layer than the HTTP layer, something like that.
It feels like you're optimizing something that somebody else optimized towards a different goal.
I see. Yeah, I guess maybe when someone tries to optimize something, they have to keep in mind that they might be hurting someone else's performance, and so we should be more inclusive between the two.
I think they were the ones being uninclusive.
But yeah.
Okay, hello, this is Zihao. Why do you choose Nexus 6? Why not some newer phones?
So at the time, it was a year and a half ago, or 2 years, that was the best phone that we could get on the market.
So you started the experiment really early?
Yeah, a while back.
Okay, thank you.
Okay, let's thank this part. I left a slot in case anyone had any questions or wanted to make any observations, but we could also wrap up early. We're going to give certificates to Mohan and Vaspol now in honoring their prizes. And there's no reason why everyone has to watch that, but I'm very grateful to you two for giving these talks. I think they were really great and really thorough and inspiring. So thank you. And thank you, IRTF Open. Okay, we have an observation from Dave Planka.
Oh, hi, Alison. I wondered if we might spend a few minutes talking about or catching the IRTF community up on what's going on, or how ARNW was formed, the research workshop. First, I want to say thank you to the ISOC people and the ACM people to putting that together. The last time I looked at it, we didn't have a committee, there was no call, and all that stuff. So a bunch of people did a bunch of great stuff to get that in order. And I guess in the spirit of sort of transparency, I was wondering if you could tell us, or one of them could tell us, how the committee was selected, what was like the reach and diversity goal, and did you meet it? I see there's an invited talk that's one of the people that's on the program committee. That's an unusual thing. But could you speak to that, or who's responsible for putting
so
that together?
I think neither of the people, the program chairs are here. So it's really a better question for them. But and in fact, so the invited talk question, I think, is an interesting one because there's quite a bit of variation between committees and workshops as to whether that's a reasonable thing to do or not. sort of the conflict of interest, whether it's okay for people who are on the committee to also be speakers. I think the reason they seeded the invited talks so early was to try to give a strong representation of some of the topics and range. With respect to the program committee, I think it's possible that that committee could grow some more. So if you were to raise a question about its composition to Sharon and Dave, it would be timely.
Okay. I mean, the overarching issue is I love the way that ANRW is different from the academic conferences, and I love the idea of running it during IETF because we're already multi-track in IETF. So that's going to be a huge improvement. And the competing idea that was floated last year was having NRW being a continuing workshop where people can keep, like, solving the other problem in academia that you keep, it's hurry up and then wait, like you hurry up to submit your thing, you wait half a year. So I love us having a different venue like this. But a couple of the things just looking to improve is we're still inviting, now in ANRW, we're inviting already published stuff there. We already do that for ANRP, so we already had a venue to do that. And I think that we should like raise the bar for ourselves to say, how did we select the committee and things like, you know, that kind of stuff. But I'm really happy that it's all in shape already and it's looking really good. The timeline to come up to a workshop in July, we've got a month to submit and then they've got 2 months to form it, so it looks really good. Mostly I'm happy with it, if you care.
I think there's also, I mean, there is a hope that there will be a fair number of these kind of lightning talks that are short, and I think it remains to be seen. And part of what everybody can do here, besides submitting yourself, is to encourage your researchy friends to bring up papers. I mean, if everybody in this room submits something and gets a friend to submit, we'll have an amazing choice. But I have had in mind that perhaps the committee should expand. With respect to the kind of continuing versus one-off, once-a-year thing, we're thinking slowly about the idea of about a bunch of those types of ideas. And I'll get you involved in that conversation, but also people in this room. We're looking to try to increase the amount of applied network research that there is. I mean, like you've heard 2 beautiful applied network research topics today, and also Rod's topic. But many times there's a really big gap between academic research and what we could then do something and build in the real world internet and see deployed. So we're looking to just enhance those relationships in every way we can.
Okay. And you actually hit on exactly the last thing I wanted to say was to remind people to solicit for it. One carrot you can use for people, one thing that's nicer about ANRW than say IMC is the talks are recorded and we're building this huge library of awesome presentations by those people. So some of the students that I've solicited to come to IETF for MapRG or something, I say they end up having this talk that's on their webpage afterwards where somebody can see them in action doing that stuff. I'm also asking IMC to come up to raise the bar for themselves to start doing that.
You should actually mention that you are one of the 2 chairs of the MapRG research group, the measurement and analysis for protocols. So this is a very parallel case to the rest of it. It's sort of like a recursive, the IRTF contains another IRTF.
Yeah, it's just a measurement subset of what could be at ANRW.
Yeah.
And then the last thing is the program committee. It looks really good. It's like there's a third women on it. Maybe it looks like about a third of the people are IETF participating academics already. So it looks like somebody did a really good job, but we should tell people how we're doing it.
Okay, sounds good. Okay, anything else anyone wants to bring up before we send you off to lunch? Okay. All right. Well, thank you for coming. See you on our mailing list. See you tonight. I'm going to give another little bit of an overview tonight, hopefully more successfully in the analog department. Oh, and there should be another blue sheet. If someone can provide the other blue sheet, that would be helpful.